The broadcast is now starting. All attendees are in listen-only mode.
Hey, welcome everybody. Coffee with Caleffi. Thanks for tuning in today, and of course, thanks for your continued support of Caleffi. So we've got a great presentation today. I'm proud to have John Siegenthaler back with us. I'm sure many of you know John. He's a superstar in our industry. He's an engineer and an educator and a mentor to a lot of people. So we've got the right guy in the right position, and we've got a great presentation for you today. So let's get rolling. Siggy, thanks for coming.
You're welcome. Good to be here. And welcome everybody. I understand we've got a pretty good sized audience today, and we're going to be looking at a couple specific topics in the general context of temperature control and domestic hot water. We're going to be looking at temperature protection. In other words, is the water safe when it comes out of the fixture? And we're also going to look at Legionella protection and talk about different hardware to eliminate Legionella, different methodologies for it. And a few questions we're going to take a look at today. Why is it important to know the return water temperature in a domestic hot water recirculation system? Oftentimes we focus on supply water temperature, but with Legionella, it's very important that we know the temperature all the way through the system to confirm that we've reached conditions that assure that we've killed Legionella. With mixing, what's the difference between an ASSE 1017 and a 1070 mixing valve? We'll take a look at that with some schematics. What are the advantages of thermal disinfection compared to other methods of disinfection? You'll see there's actually several other methods, and we'll compare and contrast those. We're also going to look at recirculation because it's part of the overall system. And we'll look at how does a variable speed pump work into a domestic hot water recirculation system. And since we're going to feature thermal disinfection, where we're taking water to relatively high temperatures for a period of time, we want to make sure everybody understands how are the fixtures protected during that thermal disinfection cycle. And then finally, how can thermal balancing work into the picture? So we'll look at these different elements in a domestic water system, and then towards the end, we'll build them into a common system. The reference for today was Hydronics number 22 that came out back in January. You can get that from the Caleffi website or sign up, get a subscription to it, and get it mailed to you in hard copy. So let's start with water heaters. I'm sure many of you have tank type water heaters, either gas fired or electric. And you know, an average person on the street may think if I simply set the dial on the thermostat of the water heater, I should have protection against high water temperatures. And that actually is not true. To start with, most of these thermostats are not very accurate. If you take a look at this thermostat here, this upper image, you'll see it has some pretty subjective settings on it. Hot, warm, vacation mode. What temperatures do those correspond to? For example, does the hot setting guarantee that nobody's going to get burned on a faucet? And actually, a recent article that came out in Plumbing Engineer magazine described how model building codes do not recognize water heater thermostats as acceptable means of controlling hot water delivery temperature. In other words, setting a thermostat for what you might think is a certain temperature is not accepted as a guarantee that when that water comes out the tap, it's going to be at a safe temperature. And there's also time lags between when the water in the tank reaches a certain temperature and when the thermostat that's measuring that temperature actually actuates. And scale accumulation on the thermostat can be one thing, just the thermal mass of the thermostat itself. And temperature overshoots in the range of 11 to 15 degrees Fahrenheit are common. And one particular situation that's problematic, repetitive short draws of hot water that are just long enough to turn the burner on or turn the element on will cause a progressive temperature stacking effect at the top of the tank. And there's actually been measurements where the water temperature at the top of the tank under those conditions can be as high as 30 degrees above the thermostat setting. Now, there's also the fact that water heater thermostats are very easy to access. It's usually just a matter of a couple screws and you're into the electric thermostat. And of course, the dial on a gas-fired water heaters is openly accessible. And at times it's accessible to people that really shouldn't be making those adjustments, especially if somebody is not happy with the hot water delivery rate for whatever reason. Maybe there's been 4 or 5 showers in close succession. Somebody feels there's just not enough hot water. So they overreact, they go down and turn the thermostat up high. And of course that in an otherwise unprotected system could very easily lead to a scald. So one of the situations, I know I've encountered this several times, and we actually have a poll question coming up on this. In commercial buildings, especially restaurants, fast food vendors, where there is some type of water heating device that is set to a relatively high temperature for sterilization purposes. In some cases, the lavatory facilities in that restaurant would just tee into that tank, and there may not be any type of temperature control device between that sterilization temperature that's intended to go into the kitchen area versus what's going into those bathroom lavatories. And you know, I raise this as a question. Have you ever been in a washroom in a restaurant or some other type of facility and found that when you open the hot water faucet that you would easily be burned if you kept your hands under that faucet? And that's actually our first poll question. So have you been in a commercial facility where hot water temperatures from a lavatory faucet would be capable of serious burns? And Woody's running that poll right now. We'll get the results, and then Bob, I'll let you talk about the results quick.
We'll find out here in a second. Yeah, by far 67% said yes and 33% said no. So
okay, so 2 out of 3 people have been in a similar situation. And of course, that's a liability on the part of the building owner. So it's something that really shouldn't occur, but it does occur, and it speaks to the need to have a temperature control device. A 1070 rated ASSE mixing valve would take care of that. Okay. Now, other potential sources of high water temperature, certainly if you're working with solar domestic water heating systems, you know that especially in the summer, 2 or 3 sunny days in a row with minimal draw, those tanks can easily reach 180 degrees Fahrenheit. So again, a direct line from that water heater off to a fixture could certainly put scalding hot water to that fixture. And systems we've been working with lately, a lot of biomass, wood-fired boilers and pellet-fired boilers, they commonly heat thermal storage tanks into that high temperature range, maybe 180, 190 degrees. And if you're drawing energy from that tank through some type of a heat exchanger for domestic, you definitely want to have a thermostatic mixing valve, and you'll see that detail over here on the far right side. An ASSE, this would be a 1017 mixing valve. Now, there are a number of graphs that are out there that show relationship between water temperature and time, and how that can lead to a partial burn, a first-degree burn, or a more serious second-degree burn. And just a few statistics here. Adult skin exposed to water at 110 degrees, you pretty much can do that continuously without risk of burns. But once you go over 110 degrees, that burn probability goes up very quickly. So 130 degree water, about 10 seconds to cause a first-degree burn on an adult, and continued exposure to that would lead to second and third degree burns. High water temperatures like 160 and higher could instantaneously lead to a first degree burn. And children and older adults, their skin texture is such that those burn times can be half of what we just discussed. So, you know, you think about infants in a bathtub that might have their hands on a faucet like this, or an elderly person in a shower where the temperature might go up quickly for some reason. The question is, can they react fast enough to get to that faucet and prevent that burn? And obviously there's been unfortunately, cases where that hasn't been the case. So it's a very serious situation. Now, one of the mixing devices that's available for controlling the water temperature leaving the water heater, that would fall under the ASSE 1017, what's called point of distribution thermostatic mixing valve. And there's several different variations on a product like this. This is one of the more recent variations. This is a Caleffi product that involves an ASSE 1017 mixing valve with some corrugated stainless steel tubing and another fixture that goes into the cold water line. And this can be ordered different ways with different types of connections, but with a press connection, you can actually install this without making any soldered connection. So on an existing system, it would be possible to disconnect the piping, put this in, use press fittings, and put this together relatively quickly, and it provides that point of distribution temperature protection. Now, in larger systems, there are higher flow capacity mixing valves. Again, this type of valve that you see in the center here, going up to, I believe, up to a 2-inch pipe size. And then for larger commercial installations, one of the modifications of using just a single valve is what's called a high-low mixing station. And if you look at that, you'll see there's a large ASSE 1017 valve paired up with a smaller one. And the idea here is that under relatively low flow rates, the small valve will handle the mixing. And then as the demand for hot water increases, you'll start to build up a pressure differential between the lower portion of this assembly and the upper portion. And that's where this differential pressure valve detects that differential pressure is building up, which is indicative of higher flow rates. And it starts to allow the larger mixing valve, which has a higher CV value, a higher flow capacity, to supplement the flow going through the smaller valve. So the idea is to allow a wide range of domestic water flow rates and still provide full thermostatic protection. A wider range than what a single valve could do. Okay. Now, the other type of thermostatic mixing valve that's often used in domestic water systems is called a point of use versus point of distribution valve. Point of use valve would fall under ASSE 1070. And I'm just showing a simple domestic water recirc system here where we've installed an ASSE 1070 listed valve on both of these fixtures, both of these lavatories, another one over here. But I also want to point out that some shower head fixtures, some fixtures come with built-in thermostatic protection today. That would fall under ASSE 1016. So when you have a fixture that has ASSE 1016 built into it, it's not necessary to put another thermostatic mixing valve. And as you can see here, there's a combination of functions, but ultimately all 5 fixtures that are served by this hot water distribution system do have point of use temperature protection. Okay, and there's an example of a 1070 valve installed with some flexible tubing under a lavatory. And again, the 1016 standard refers to shower valves with built-in thermostatic protection. Now, the next category, and a new category, relatively new in North America, is motorized mixing valves. Of course, motorized mixing valves have been around for a long time in hydronic systems, and this is a no-lead version of a 3-way ball valve with a motorized actuator, a 24-volt actuator. And this brings several different features to play that were not available on the standard thermostatic mixing valves. It allows a much wider range of flow control, and it allows pre-programmed functions such as thermal sterilization. Okay, so we have a motorized valve with an intelligent controller, and that controller has built-in routines that you can set up, or that controller can be tied to a building automation system through Modbus. So here's a photo that shows the Legiomix product built in along with the controller that goes with it. We'll take a closer look at that valve here. I mentioned it's a three-way ball valve, so it has very high flow rate capability. The specs right out of the spec sheet here, these valves are available from 1-inch pipe size up to 2-inch, and you can see the CV values are fairly high. These would be higher CV values than what would be available in an equivalent pipe size with a thermostatic element. You also see down below here, there's a temperature sensor that actually taps right into the flow stream. So we have a solid state temperature sensor that goes back to the controller. So this valve always has feedback on what the mixed water temperature is leaving the valve. And it also, because of its design, it compensates for very low flow rates. We actually can have a complete close off of the hot port. With a thermostatic valve, sometimes we have to use balancing valves to make sure that we don't get temperature creep in the distribution system. That's not necessary with this motorized valve. So now we're going to turn from temperature control into Legionella. And one of the graphs that actually we researched when we put Hydronics 22 together, I was quite surprised at this when I found it was a National Notifiable Disease Surveillance System. Just looking at from the year 2000 up to a couple years ago, what the increase has been in the incidence of Legionella. And these numbers over here, cases per 100,000 population. And you can see that over roughly, well, a little more than a decade, the incidence of Legionella disease has almost doubled. And where does this Legionella bacteria exist? Well, it exists in both public and private water supply systems. It can also exist in a biofilm inside a pipe. So this photograph, it just shows an accumulation of some biofilms as well as some sediment. And think of these as little crevices where this bacteria can actually reside. And it's important to understand that because we have to do more than just bring the water temperature up momentarily. We have to bring the water temperature up and sustain that condition for, well, depending on how high the temperature is, typically 10, 15, maybe 20 minutes to allow sufficient time for that temperature to reach into the matrices, so to speak, of these biofilms and make sure we get a complete kill on the bacteria. Legionella is actually in water. I'm sure all of us have ingested water that has Legionella bacteria in it, but we don't actually acquire Legionnaire's disease by drinking water. It's acquired through respiration. So a shower head, the mist that's created by a shower head, when that's inhaled, if there's certain levels of Legionella, that's basically how it gets in the lungs. And it can develop into a pneumonia-like condition, and it's an example of a Legionella pneumonia X-ray, and it shows a very congested lung situation. So it's a serious disease. It is on the rise. It is something that the industry as a whole, the plumbing industry, is taking a very concerned approach to. ASHRAE standards have been developed on this. And I'm sure many of those that are listening today, you're interested in creating methods that can assure that you're sterilizing your systems against this. So that leads to the next poll question. How many of the commercial domestic hot water systems that you either design or install include a specific means of preventing Legionella growth? So we'll run that poll now.
And that's a good question that you came up with for that, Siggy. Give you here about 10 seconds and see what the consensus is on this one. 4 choices, so we'll see how spread this is. There we go. That was quick. So only 15%, most 19%, some 39%, and 27% for none. So that's a bit of a shocking statistic.
Yeah, and I'm sure there could be some differentiation between a commercial application, residential applications as well. But commercial facilities, hotels come to mind. Obviously, a Legionella outbreak there, or an outbreak in a elder care facility could be very, very devastating. Okay, so let's keep moving. okay? Legionella bacteria maintained at acceptable levels. There's different ways to control Legionella. Chemical injection, either a chlorine or a chlorine compound, chlorine dioxide. This is an example of some hardware and some chlorination chemicals that would be periodically injected. Another means here is periodically flushing all portions of the system. Basically, a flush of water trying to get rid of any water content in the system that might have Legionella in it. Exposure to ultraviolet light. You can find hardware that basically the cold water would pass through and be irradiated with ultraviolet light. And ozone, good strong oxidizer. There's an example of some of the equipment that would be used to inject ozone into the water. And then finally, where we're going to focus today on thermal disinfection, the basic idea of periodically raising the water temperature in a recirculating domestic hot water system high enough and long enough to kill the bacteria. So we'll start with the temperature relationship to how Legionella exists. So you can see that below roughly room temperature, below about 68 degrees Fahrenheit, Legionella can survive, but they're dormant. It's not really a concern in a cold water system. But once we start to warm that water up, anywhere from about 95 to 115 degrees Fahrenheit, that's considered the ideal growth range for Legionella. Above that, the ability of Legionella to survive depends on the temperature and the duration of that temperature. And you can see on the scale here, at roughly 130 degrees, Legionella die within 5 to 6 hours. Well, we're probably not going to maintain 131 degrees for 5 to 6 hours in a recirculation system. It's possible, but that's a relatively, I guess I'd call that a slow kill. Taking the water temperature up farther to 140 degrees, we significantly reduce that time down to about half an hour. At 151 degrees, assuming that temperature reaches the bacteria, and again, think about the biofilm, the scale. It's not enough to just expose it instantaneously to 151 degree water, but within 2 minutes, you would be killing the Legionella. And then from roughly 158 on up, you get a very effective kill very quickly. Now, there may be specific code requirements that either exist today or are going to be developed that are going to give specific numbers on times and temperatures to ensure a good sterilization cycle. So in the absence of those, some numbers that we've put together, at least 158 degrees, and that would be in all parts of the domestic water distribution system, including the recirc return line, for a minimum of 10 minutes would be considered an effective kill cycle for Legionella. You'll see as the temperature goes down, the length of time goes up. So at least 149 degrees, again, in all parts of the system for 15 minutes, or 140 degrees for 30 minutes. And again, these are guidelines to give you some idea of what time-temperature relationships are. If there are specific codes in your area, obviously those would take precedence. Now, thermal disinfection, this is a technology that has been in use in Europe for quite a while, over 15 years, and it's the most commonly used form for Legionella control in Europe. So let's look at some of the benefits of it. There's no need to purchase, transport, or store aggressive chemicals. Chlorine is a very aggressive chemical. And again, just the storing of that chemical, the vapors coming out of that chemical, for example, one of the things we've learned over the years, never store chlorine in a mechanical room where there's an atmospheric boiler that could get into the boiler and quickly turn into a hydrochloric acid and cause severe corrosion. So chlorine is kind of a nasty chemical to have on site and to transport, okay? With thermal disinfection, you don't have to worry about overdosing or underdosing with whatever the disinfection chemicals are. There are no chemicals needed. And there's actually no need to flush the plumbing after the dosing. So that's important in areas where water is in short supply. We don't need to flush water out of a hot water distribution system as part of a thermal disinfection cycle. Okay. Now, there's also no concern about human or animal sensitivity to those disinfection chemicals. Again, these chemicals are going to be in higher percentages than what normally would be in municipal water during this disinfection process. And as such, there could be some sensitivities to those higher levels of those chemicals. There's no need for cleaning the disinfection apparatus, which is a requirement when you're working with a UV disinfection system. Sometimes there are some very high performance ultrafiltration systems that are used to get bacteria out of the water. And again, there's maintenance, there's cleaning associated with those, replacement of filters. No concern about ozone. Ozone, again, is a very strong oxidizer. It can react with metals, plastics, elastomers in the system and react in such a way that it degrades those materials. Okay. And in a properly designed system using thermal disinfection, there's no change in water temperature or water chemistry at the fixtures. Now, you might be wondering, how can that be? Well, remember, we need to protect those individual fixtures with 1070 mixing valves or 1016 shower heads. So we are going to bring that recirculation loop up to that high temperature and hold it there for several minutes. During that time, those fixtures are still available, and we have to have those point of use thermostatic valves to protect those fixtures during that time. And again, concern about potential chemical reactions depending on what the disinfection chemicals are. How will they react with copper? So you can see there's a lot of benefits to using thermal disinfection. Okay. Now, earlier I mentioned it's important that we maintain these time temperature relationships through the entire distribution system. And for example, if we start releasing water from a Legiomix electronic mixing valve here, we might release that water. I'm just going to pick a number, let's say at 145 degrees Fahrenheit. Well, there's going to be a temperature drop in that distribution system. And actually referencing back to Hydronics 21, there's methods and data in Hydronics 21 that shows you how to calculate what those temperature drops are. Certainly it depends on flow rate, it depends on the length of the piping system, the size of the pipes, and whether or not they're insulated. But let's say that we come back at a temperature that is less than the time temperature relationship that we've established for successful Legionella sterilization cycle. Well, you know, we may have protected the supply side of the system, but we have failed to meet the time temperature relationship on the return side. So the Legionella product does have a temperature sensor built in that can be installed on the return side of the recirculation system, and the electronic controller can verify whether or not there's been a successful time temperature cycle executed. If it hasn't executed properly, there's a relay contact in the controller that can turn on an alarm. So this device does log whether or not these sterilization cycles are successful, and if for whatever reason it was unsuccessful, perhaps it's a failure of the heating element in the tank, whatever the case, at least there's going to be an immediate indication that that sterilization cycle hasn't been properly executed. Okay. And one of the submitted questions, what is the process of cooling down the domestic hot water system after the thermal disinfection cycle is complete? Well, normally we would just, the mixing valve, the Legiomix would go back to its normal temperature sensing, or setting rather, and the water in the loop is going to cool down over time, either through usage or just heat loss through the recirculation piping. Remember that the 1070 valves are in place at the fixtures, so it's not really a concern about bringing that water temperature immediately back down to a, what I'll call a safe distribution temperature, as long as those 1070 valves are installed on those fixtures. Okay, so again, same slide we looked at earlier, having the 1070 valves or the 1016 protected shower heads on each of the fixtures as part of a complete system where thermal disinfection is going to be used. So let's do one more poll question here. How many of the commercial domestic hot water systems that you design or install include recirculation? So we'll stand by on that one.
I think in some areas, see, that's required. I think in California, anything over 50 feet of distribution piping is required by code to have a recirculation line, probably more for water, you know, wasting than
right.
Thinking about Legionella, but they've got the opportunity there. So what do we have there? We've got 38% all, most 39%, some 21, and none 2%. So that's interesting on the none.
Yeah, again, commercial systems versus small residential systems, we'd more likely see recirculation. And large residential systems, especially where fixture groups are spread out through a building, I would think today it's fairly standard practice to set up recirculation in those systems. Okay. Now, another aspect of a commercial or large residential recirculation system is thermal balancing. And to kind of get the feel for this, we'll start down at the bottom here. We've got a hot water trunk line coming from our hot water heater. We've got a recirculation line that's going to carry heat, well, slightly cooler water, but still warm water back for reheating. And of course, we have cold water. And what we're looking at here is, I'll call it a riser. And the riser goes up through the building, and it could pick up, it could actually serve several fixture groups. And just an example of a fixture group would be a lavatory here and a shower head. When there is sufficient demand for domestic hot water, the amount of water that has to recirculate can be reduced. Remember that the purpose of recirculation is to keep hot water available at the fixtures at the far extremes, well, actually all the way through the hot water distribution system. If that is being done just by normal fixture demand, we can reduce the amount of flow going through that recirculation system. And Caleffi does have a specialized valve for that. It's called the thermosetter valve. We're going to take a look at how that works. Again, there's more information on that in hydronics number 21. So the way I like to describe this valve is, this valve opens and closes as necessary to ensure that the return end of one of these domestic hot water risers is at or above some minimum temperature setting. If that's occurring through normal water use, this valve will actually throttle down to a fairly low CV value. It actually throttles down to a CV of about 0.23. It's still allowing a small amount of flow through, and that's necessary so that the temperature sensing element in the valve always has current information on how that particular leg of the system is doing, all right? But again, if it's sensing this temperature, and you'll see in a next slide here how we can set this, if it's sensing that there's adequate temperature there, it's going to throttle down, and this allows you to use a variable speed pump, just like reducing flow in a hydronic distribution system using thermostatic radiator valves, or perhaps closing down zone valves. As we close off some of our zones, we can reduce the speed of that pump, and of course that reduces the energy use of that pump as well. Okay, so part of the reason to use these valves, beyond ensuring adequate hot water availability in the plumbing system, is to reduce the energy use of a recirculation pumping system. So what these valves look like? Well, it's a no lead brass body, and the basic valve has a thermostatic element in it, and you'll see a dial up here that you can set. And let's say we set that dial for 140 degrees, okay? At 140 degrees or higher water temperature, this valve would be at its minimum CV value, 0.23. And again, the valve doesn't completely close because it's necessary to have flow, a small trickle of flow going by that thermostatic element to make sure the valve continues to monitor. Now, if the water temperature is quite low, let's say we're coming out of a cold start condition on a domestic water recirc system, and our water temperature is low, that's going to be up to a CV of 2.1. That thermostatic element's going to open up and allow a good high flow rate going through there. And it's got a nice wide proportional range. So as that temperature starts to climb, you'll see that the CV value of the valve starts to reduce. So as we're approaching the set point temperature, we're actually reducing towards that minimum CV value of about 0.23. That's the basic valve. Now, the valve can also be configured for systems that are going to use thermal disinfection. And it's done by adding another thermostatic cartridge in the valve. And that modifies that curve. So the red line that we're looking at on the graph up here was the same thing we just looked at. But now, instead of staying at a minimum CV value all the way up through, it reduces down to a lower CV value. In there. It reduces to a lower CV value. And once that temperature gets up around about 100 and looks like about 155 degrees, you can see the CV value goes back up again, and it goes up to a value about 1.2 at 160 degrees. And that's there so that we can get a full flow of hot water going through the system under thermal sterilization conditions. Sorry about the phone in the background there. So again, this valve is specifically configured for a thermal disinfection system. It would cooperate with the Legio mix during a thermal disinfection cycle. Now, I've mentioned several things here that we did cover in the previous issue of Hydronics number 21. If you're interested in doing calculations on domestic hot water flow rates and how pipe size, pipe length, pipe insulation, and so forth affect it, the data and the methods are all laid out in Hydronics number 21. And another question that was submitted, I'll just read it here. It says, address desired flow rate on the recirculation return line. Experience shows EcoCircle Alpha Pump work well. It depends on the flow rate. If it's a very large commercial facility, the two pumps that are mentioned here, these are relatively small pumps. They may or may not be sufficient. So again, it's a matter of running the numbers on the system, and there's some good examples of that in Hydronics number 21. Now, early on I mentioned that one of the benefits of using the thermosetter valves is that as they throttle down, as the temperature in the recirculation branches comes up to where it needs to be, where it's sufficient, as they throttle down, of course, that is going to create an increase in pressure back at the recirculation circulator. A variable speed circulator is really ideal when it's paired up with these valves, because as that attempt to increase differential pressure occurs, the circulator, depending on how it's set, it might be set for constant differential pressure or what's called proportional differential pressure. That circulator is going to slow down, and that means reduced energy use. And keep in mind, in a commercial facility, these circulators might be running 24/7, 365 days a year. So even a relatively small pump, if there's a way to reduce the wattage down on it, that's going to result in energy savings. Okay, and again, I liken it to a hydronic system where we're either throttling down a valve in a zone, or we're opening and closing a zone valve, and we're allowing the pump to automatically adjust to those conditions. Now, we can see that over here. Let's say that we have a head loss curve for a hot water distribution system when all the thermosetter valves are wide open. So they're all at their maximum CVs. Think relatively low water temperatures, right? So the pump's at its full speed, and of course we're at a high flow rate. If we drop the line down here, we could, and we had numbers, we could look at that higher flow rate. But as those thermosetters start to function, as the hot water reaches those thermosetter valves and they start to throttle down, that system curve, that blue curve that you see here, is actually going to get steeper. So this would represent a head loss curve where, let's say, some or all the thermosetter valves are at their minimum CV values. They're just allowing that trickle of flow going through for temperature sensing. And under that condition, the circulator can slow down quite a bit. So the pump curve moves from this upper red curve down to this lower curve. And of course, that's decreased input power to the circulator. And it leads to actually one other question that was submitted. Can the 116 series, and that does refer to the thermosetter valves, can it work with a constant speed pump as well as an ECM? And ECM would imply variable speed. And the answer is yes, it can. You are going to get an increase in differential pressure across a fixed speed pump as you would in a hydronic system with starting to close down zone valves. That's not necessarily a problem, but it's not as good as a scenario where you have an intelligent pump that can feel that attempt to go to higher pressure, reduce motor speed, and reduce energy usage in the process. So let's do one more poll question here. Do you use variable speed circulators on the recirculating domestic hot water systems that you design or install?
Yeah, and that's a good question, because some of the manufacturers are just coming out with either stainless or low lead versions that you can use them on domestic water systems. So this will be interesting to see if people are embracing those that technology in domestic water recirculation applications. So,
okay.
Oh, yes, 38%, no, 62%. So again, that might be an availability issue too.
Yeah, and we are seeing several manufacturers now that have hydronic variable speed pumps also have got stainless steel versions of those pumps. So I suspect the use is going to go up just given wider product availability. So let's put this all together. I'll call this the total system concept. Okay, we'll look at what we're trying to provide here. Well, we want immediate availability of hot water at all the fixtures. That's the main function of a recirculating system. And you know, even without using the term recirculation, that's an ideal condition. You open a faucet and within a second you have hot water, regardless of where that fixture is located in the building. And we want to reduce water waste. That's a major issue today, especially in Western states, by avoiding situations where somebody opens a faucet, lets the supposedly hot water, which isn't hot because it's cooled off in a non-recirculating system, they have to flush that down the drain and waste it until the hot water finally gets to that fixture. So we're trying to reduce water waste. Okay. We want to make sure that we deliver water to all the fixtures at conditions that are not dangerous, typically less than or equal to 120 degrees on fixtures intended for water going on skin contact. And the sterilization function we talked about, we want to ensure that these delivery systems don't pose a threat due to especially Legionella. So you can see several objectives in the overall system. And I've put together here a schematic that shows it. So we'll start down here with we've got a tank type water heater. We're using the Legiomix mixing valve. I'll call it the master mixing valve. Recall that can be set up with thermal sterilization programming. It can be set up as just a supply temperature control valve. That would be a very simple minimal function of the valve, but the real strength of this valve is that it's programmable to give you thermal sterilization. So we go out through our distribution system. I've shown a couple risers here, and you'll see the fixtures in these fixture groups either have an ASSE 1070 point of use mixing valve, or the assumption that a shower head might have an ASSE 1016 thermostatic protection. So all the fixtures are protected during the thermal sterilization cycle. We're including the 116 thermal setter valves on the return side of each of these recirculation risers. Again, they are going to independently adjust the flow rate through the risers to maintain adequate flow so that the last fixture group has hot enough water to it, but then they'll start to throttle down. And the last element that completes the picture here is a variable speed circulator that is going to respond as those thermosetter valves modulate open and close. So you can see there's quite a bit going on here from temperature protection standpoint, verification of time temperature relationships during a thermal sterilization cycle, minimizing pump energy use by not overflowing on a recirculation system, and finally complete temperature protection at every fixture, especially when that water temperature in the recirc system is elevated during the thermal sterilization cycle. And these components are all available, fairly easy to put these systems together.
So with a little time left, Mark, I think, has been kind of monitoring the questions that you might have typed in while we're going through this, and maybe he'll pick a handful that we can get to, and Siggy or Kevin or myself will, or Mark will answer them for
Yeah.
us. So,
yeah, very good. Yeah, nice job, John. A couple of questions. They're coming in fast and furious, actually, as people type them in here. But one question is, when you're doing recirculation and thermal disinfection, what is a typical temperature coming back to the hot water heater on the return leg that you want to stay above?
Well, yeah, it's going to depend on time as well. We talked about, I believe at 140 degrees, it was about 31 minutes. So if the water temperature on the return side was 140 or higher, and it was maintained for at least 31 minutes, that would be an example of an adequate or complete sterilization cycle. So higher water temperatures would allow shorter times. At 158 degrees on the return side, I think it was 10 minutes. So, and those temperatures can be estimated based on, again, some methodology that we put in Hydronics 21, looking at pipe lengths, insulations, and so forth. Essentially, what a designer is going to do is pick what is the acceptable maximum temperature drop from where the water leaves the mixing valve, the master mixing valve at the point of distribution, to the farthest fixture served by the plumbing system. And common numbers there in a range of 5 to 10 degrees Fahrenheit. So if we went with 10 degrees Fahrenheit and we wanted to ensure that we had, let's say, 158 degrees on the return side, we wanted to go with that 10-minute sterilization cycle, we would need to have at least 168 degrees, 10 degrees higher on the supply side. So again, I would pick whatever the criteria is on the return side, the temperature and time, and make sure that the supply side of the system is set so that we're going to achieve that. And again, Legiomix, of course, if you don't achieve it, it's going to give you an alarm to let you know.
Very good.
I think that'll be based too on the return piping. If it's not insulated coming back, you could have quite a bit of temperature drop. Thinking of a big hotel or something like that, or a big building where they didn't insulate or didn't insulate well enough that return. I mean, that's a heating system basically. So you're going to make sure that that's why the sensor on the return of the Legiomix is so important. It assures that it came all the way back to the tank at that increased temperature.
That's right. Actually, the methodology that has been used to kind of standard practice. We actually don't look at the heat loss of the return, but to your point, they should, because it's there and it is going to reduce that temperature down on the return side of the system.
Very good. A couple other questions here concerning thermal disinfection. If you have risers in your building going out to legs running down, what are some piping methodologies to make sure that you get thermal disinfection quality water as close as possible to your fixtures, basically to minimize dead legs?
Yep, that's a really good question too. And the simple answer is to, as you just said, minimize the dead leg, the distance from the recirculation portion of the system actually to the fixture. So getting the recirculation piping in close proximity to a fixture group as kind of a generic answer to that would help. I know there are some fittings, Venturi fittings and so forth, that are designed to try to get that in a little bit closer, but to my knowledge, those have actually not been tested with the thermosetter valves to know exactly how those two would interact. So I would say just good piping practice would be to get that recirculation leg as close to the fixture groups as possible.
Another question came in. I have an application that I don't need thermal disinfection, but I'm interested in the digital mixing valve. The question is there any means for prevention of scale buildup on the Caleffi Legiomix?
Well, it's a ball valve, so it's kind of a self-cleaning valve as it modulates. And beyond that, if Kevin's available, maybe he has some input on that.
Yeah, John, the program has an automatic cycle that it runs every night. It does a full stroke, closed and back open, just to wipe away any debris or buildup or scale on the ball of the seat.
Good.
Thanks, Kevin. Another question just came in. It's in regards to balancing hot water recirculation lines. The question is, I'm familiar with more typical mechanical type balancing valves, not so familiar with thermostatic balancing valves. Is this product reliable, and can you speak to any history on this? So maybe.
Well, I guess the way I look at it, it's a relatively new embodiment of a thermostatic element concept that's been around for decades. And Caleffi's built millions of valves with thermostatic elements in it. So it really relies on a technology that's been very well established. We're essentially packaging that actuator into a no lead, specifically designed, a no lead brass body for that purpose. And to his earlier question too about using mechanical or just manual balancing valves, again in Hydronics 21 we do talk about the possibility of using manual balancing valves. They're out there, and actually Caleffi has product available for that. The difference is going around and having to put a manometer on those valves and basically going through a balancing procedure similar to what you do with a hydronic system, where when you make an adjustment on one valve, you really have to go back and verify how far the other flow rates have drifted based on that adjustment. So from a convenience standpoint, and from the standpoint of what's the objective, the objective is to keep a temperature criteria established at the far end of those recirc risers. So it's a valve that's really specifically designed for what the objective of domestic water balancing is, which is different from a hydronic heating system or a hydronic cooling system. It's about maintaining a temperature versus controlling a rate of heat flow. So I would have to say, just based on the experience and the history of thermostatic elements, they would be a reliable product.
I would certainly say you add to that you want to put in this, don't bury it in a wall somewhere where somebody, number one, didn't know it was there. If it did have to be serviced someday, that they need to be accessible. Typically, they're going to be back at the mechanical room where all these branches tie back in, but certainly in a big building, they could be spread out throughout the building. So you want to make sure that somebody can get to them later to service them if that needs to be the case.
Good point.
Okay, looking through the questions here, some more questions. Concerning the operation of the control for the digital mixing valve, can you comment on any interfacing with the hot water heater itself as it relates to water temperature regulation for the thermal disinfection cycle? I guess that's referring to inputs and outputs, and maybe Kevin, this might be something that you jump in on if you have an answer to that.
Sure. The controller has relay outputs. One of the relays is called a thermostat relay, and that would typically be wired to a second aquastat on a water heater that's set at a higher temperature range. So you can wire that in parallel and adjust the water heater temperature to a higher level using that relay if you want to. Does that answer the question, Mark?
Yeah, I think it was trying to understand. Yeah, the question I think was in terms of the communication back to the water heater for telling it to turn on or turn off in order to regulate the temperature during the thermal disinfection cycle. So, yeah, thank you.
Yeah, that relay energizes. There's another relay too that you wire in parallel with if you have on your recirculation pump a timer or an aquastat. The relay number 2 in the controller wires in parallel with that control, so that you send a relay contact to the heater to elevate the temperature, and then you also make sure the circulating pump is running as well.
Very
I
good.
would add too, this is a good information for if any manufacturers are online today that are, make water heaters and stuff like that. This is something they certainly want to consider, is making that function available in their water heaters, that it has that second stage available in there, whether it's a dual aquastat or an additional aquastat. That could be, certainly with the microprocessor controls these days, that could be programmed in there fairly easily, that you would just have to give that a call or give that a signal, and the water heater or the boiler or the indirect tank or the heat exchanger, whatever it might be, knows it's time to go into that mode. And of course, our control could keep track of that. In fact, data log that in fact did happen. So we certainly need that function available.
Quick comment from Mark here concerning an earlier question on the reliability of the technology. Caleffi has been in Europe marketing thermostatically controlled balancing valves for hot water recirc for quite some time. So the technology is more developed in Europe, probably as a relation to the high cost of energy. But back here in North America, in addition to Caleffi, there's at least 2 other manufacturers in the market space in North America. And by evidence of the displays in Chicago for the AHR show, a couple more coming down. And so I think the engineers and designers can look to, over the next couple of years, several makes coming into the marketplace for balancing using thermal means rather than mechanical means.
Good point.
Okay, let's see here. I think we're at the top of the hour, Bob and John, and we've got a few more questions, but we can get back to the folks that we can't get to on this directly. And with that, I'll hand it back to you, Bob, to wrap things up.
Yeah, well, thanks everybody for hanging in there today and for thinking about Caleffi, and spread the word. And we'd love to see you again. And hopefully I'll be visiting your town soon and be able to shake your hand and say hi. And thanks to all our reps and stuff that I saw tuned in today for participating. And thanks, Siggy. This was great. And we'll look forward to some more presentations later in the year. I think we've got you keyed up for a couple more. So thanks for putting all the time and energy into making this a big success for us.
Sure, my pleasure.
All right, everybody. Until next month, happy sales. Bye-bye.